Hey guys, this is Professor Janacek, and I want to go over some examples of finding partial derivatives. Let's take a look at example 1 here. We want to find the first partial derivatives for f of x. Y is equal to y to the 8th plus 2x to the 6th plus 2xy. All right, so first partial derivatives, yes, that's plural because we have a couple of them. We'll have the first partial derivative with respect to x. So that means I'm going to treat the y terms, the y bits, as constants. Those remain constant. All I really need to worry about is taking the derivative of the x part, right? Just worry about x. So the first term here, y to the 8th, there are no x's in it. It is completely constant with respect to x. So the derivative of a constant is 0. Okay, that means I don't need to do anything with that bit. Moving on to the second bit, the derivative of 2x to the 6th. It's exactly as you would expect. We can use our power rule. We end up with 12x to the 5th. Right? And finally, that last piece there, 2xy, remember I'm going to treat y as if it were a constant, so it just kind of stays there. And so the derivative of 2x would simply be 2, but don't forget we have that y still attached there, so we get plus 2y. And there's the first partial derivative with respect to y. How about the first partial derivative with respect to, first partial with respect to x. Now let's take a look at the first partial with respect to y. So now I'm going to just look at the terms with the y's, the x bits, those parts right there. Don't have to really concern myself too much with those. I'm going to treat those as constants. All right, so the first term, y to the 8th, will take the derivative just like you would expect using that power rule. So we get 8y to the 7th. Oops, that should be a 7. There we go. The second term there, 2x to the 6th, that doesn't have any y, so this is a constant with respect to y. The derivative of a constant is 0. That doesn't give us anything. All right, and the last term, 2xy, again, taking the derivative with respect to y is just the coefficient, so we end up with just 2x. And there you go, the first partial derivatives. Example 2, we want to find now the second partial derivatives of f of xy equal to 2x to the 5th y squared plus x squared y. We will need to start with the first partial derivatives. Okay, so the derivative with respect to x. Again, I'm just going to concern myself with the x's. Those y's, kind of treat them almost as if they're not there. They are still there. They're constant. So let's see, what do we get? The first one, we end up with 10x to the 4th, but then you just keep that y squared on there. And then x squared y, again, looking at just the x's, I get 2x, but keep that y there at the end, right? There's the first partial with respect to x. The first partial with respect to y. Now I'm going to treat the x's like constants, just kind of holding on to those in a constant fashion. So the first one, we get 4, keep that x in there, 4x to the 5th y. And then the second term here, again, that x squared kind of is my constant, stays there. Of course, the derivative of y would be 1, but need to multiply that by x squared, so we end up with 4x to the 5th y plus x squared. Those are the first partial derivatives. Now we need the second partial derivatives. Let's take the second partial with respect to x we'll start with this first partial. So again, looking just at the x's, those y's will stay constant. So we end up with 20. Actually, let me go ahead and include the notation properly. We get, oh wait, with respect to, what are we doing? With respect to x the second time, that's going to be 40 x cubed y squared plus 2y. Again, treating those y's as constants. Now looking at the same first partial with respect to x, let's take the second partial with respect to y. So still looking at this one, but now I'm going to take the derivative with respect to y. So now the x's remain constant in this. And that gives us 20 x to the fourth y plus 2x is the constant we have there at the back. Okay, let's take a look now at the first partial with respect to y, and then the second partial also with respect to y. So looking at this one now, take the derivative with respect to y again. All right, with respect to y, so don't need to concern myself too much with that x, just the y. So we end up with 4x. Notice x squared, that's constant with respect to y, so that the derivative of that goes to 0, so we end up with just 4x. Oh, there's a 5 on that x still. All right, and now if we've got the first partial with respect to y and the second partial is with respect to x, right? So again, I'm looking at this one, the first partial with respect to y. Now I'm going to concern myself just with the x's. So this y here, I'm going to treat as a constant. So using our power rule, we get 20x to the fourth y plus 2x. All right, well, there you go. Not too bad. Yes, I do notice that, look, these two are the same. There is a connection there. We will talk about that later. All right, so there are second partial derivatives. Ooh, can be a little tedious. And then, of course, you see if you took third partial derivatives, each one of those would have a couple of third partials, each with respect to x and y. So it can get pretty tedious to take second and third or fourth derivatives here. All right, let's move on to example 3. We want to find the first partial derivatives of g. Notice g is described by 4 variables, w, x, y, and z, and it is the cosine of w plus x times sine of y minus z. Oh dear, that looks like it's a product. Will we have to use the product rule? Well, let's take a look. Let's start with the first partial with respect to w. Notice the only place I have a w is here in the first one, so I only need to take the derivative of cosine. Well, that's not so bad. The derivative of cosine is negative sine. Keep that argument as is. I would have to use the chain rule, but the derivative of this argument here is just 1 with respect to w. So nothing I need to worry about there. I do need to go ahead and keep this bit here in the back. It is a constant, so it still stays there. All right, well, that wasn't so bad. Let's try the first partial with respect to x. The only place I have an x is here. So again, taking the derivative of the cosine function, we get negative sine again of w plus x. Again, chain rule, the derivative of the inside function, if you will. That argument is just 1. Don't need to worry about that, but I do need to keep this sine of y minus z, this constant. Keep that there attached to it. All right, well, that's not so bad. No product rule yet. Yay. All right, how about the first partial with respect to y? All right, now the only y I have is there in the second one, which means this first bit is a constant. I'll just write it down. Cosine of w plus x. But now what's the derivative there in the back? What's the derivative of this? Well, the derivative of sine is cosine. And then, of course, chain rule, I'd have to take the derivative of that argument, but the derivative of y minus z with respect to y is just 1. No problem there. Okay, looking good. We've got one more to go. The partial derivative of g with respect to z. Right, again, my z is just here in the back, which means that first bit here is a constant. Let's just write that down. No problem. Actually, that's an equal sign. All right. Okay, there we go. And now the derivative here in the back of sine is cosine of y minus z, but chain rule says I need to take the derivative of my argument. Notice the derivative with respect to z of y minus z. Notice I'm taking the derivative of negative z. That would be -1, which means, oh, I need to put a negative out in the front of all of this. I could have multiplied that -1 in the back or here in the front, either spot. I'll just go ahead and put it there in the front, and there you go. All right, not too bad, I hope. Enjoy.